So right now I'm going to go through the Newton's State Fair lab, which I did as a series of demonstrations to the class. So I'm going to help you fill this out here as I go through each of these demos. So what you'll want to do is I'm going to explain what goes in each spot, and of course I'm going to be talking fast, so you will have to slow it down, rewind it. Luckily it's a video, so you can do all that with it. So first of all, who's in your group? Well, that would be everybody. That would be the class. So you can just put class. Then it asks for the name of Newton's first law. That is on your notes, but in case you don't remember, a little memory cue for that is that Newton's first law says that objects in motion stay in motion, objects at rest stay at rest. The reason they do that is because they are lazy. Lazy comes from the Latin for inertia. So the reason objects stay in motion or stay at rest is because they have inertia. So then it's amply named the law of inertia. So that is the law for, that's the name for Newton's first law. Describe what happens in station 1. Well, in station 1, here we go. I'm going to take a washer, or it says washers, but I'm going to take pennies. And I'm going to put a card on top of the pennies, and hopefully you can see this. And these pennies have a certain amount of inertia, and they have a desire to stay where they're at. And so right now they are balanced. There's a balance force on the pennies, upward force of the card, downward force of gravity. It is balanced, so they are not moving. Also, the card is balanced. It's balanced by the top of the beaker, force holding it up, gravity pulling it down. I'm going to create an unbalanced force by flipping the card. The card's going to fly out from underneath the pennies, and if I do this right, the pennies, then having an unbalanced force, they'll lose the support of the card. They will drop down into the beaker. So what you're observing is flick, and the pennies drop down into the beaker. So that's what you observed. Pennies were resting on the card. I flipped the card went flying, the pennies dropped down in the beaker because they did not fly. So you're going to want to write that in there, what you observed. And then B says which washers, or in this case which pennies, had a balanced force acting on them, and explained. Well, the balanced force was when they were on the card, and then also you have a balanced force when they're in the bottom of the beaker, because they have a downward force of gravity always, but when they were sitting on the card, they had support, or the normal force of the card. Sitting on the bottom of the beaker, they have the normal force of the bottom of the beaker. So in those two positions, they're balanced. When they were falling, they were unbalanced. So C says, where were there 3 unbalanced forces? Well, there was an unbalanced force on the card when I flipped it. There was an unbalanced force that created the change in position from rest on the top of the card to the acceleration as it moved downward, and then another unbalanced force when the pennies went from moving down to back to rest on the bottom. So the unbalanced forces were the removal of the card, and then the subsequent showing up with the bottom of the beaker. And then of course the flip of the card, which caused it to move as well. The key is anytime there's motion or change in motion, there's an unbalanced force. So we had a change in motion of the card, therefore an unbalanced force. A change in motion of the pennies twice. Once they went from rest to start, then they went from moving to rest. So there was unbalanced forces associated with each of those. Now we're going to do one where we do dishes, and this one is essentially going to be, I'm going to have to come around to the front here, so I'm going to move around to the front and try to do this as close to the camera as I can. I'm going to take a beaker that has some water in it, so therefore some inertia, put a little tablecloth underneath it. Newton's law says that objects with inertia have a tendency to want to stay in position. So I'm going to pull this out from underneath it, and hopefully the beaker will stay in position. Otherwise, we all get wet. So here we go. 1, 2, 3. And as you can see, it stayed in position. But if I do the same trick with an object that has less inertia, I'll need the styrofoam cup, we're going to see a different result, because less inertia means less resistance to change in position. So if I do this one, and I can do this one from here, because I know that this with less inertia is going to move. So I'm just going to try to pull it out from underneath it. And of course, with less inertia, it has less resistance to change in motion, so it goes ahead and changes right away. So in that demo, you saw the object with the most inertia stay in place. The object with the least inertia did not stay in place very good at all. So what did a better job? removing the tablecloth, the object obviously with more inertia. That should be more of a what than a who. And then would it be easier for this to be done with real dishes? And defend your answer. Of course, real dishes would have much more mass and much more inertia than plastic or styrofoam or paper. So obviously real dishes would be easier, and your defense is because they have more mass, therefore more inertia. Alright, so as far as the inertia car, we're going to skip 5A, B, and C. But we are going to do D, E, and F. So D, E, and F have 4 free body diagrams with different forces. You're going to be looking at your paper, and I'm looking at mine here. And the questions are, which one of the following forces diagrams depicts object at rest? And list all and defend your answer. Objects at rest have 0 net force. So you're going to be looking for the free body diagrams with each of the arrows canceled out by the opposite side arrow. And you find that is true for the A one and also true for the C1. So A and C are objects that could be depicted at rest. And your defense is that rest has 0 net force. Which objects have a unbalanced force that could produce motion? And that would be the other two, of course, B and D. And again, your net force is not 0. So, and then of course, which one, E or F says which one could produce a constant velocity to the right. So constant velocity is the same as at rest in terms of the magnitude of the arrows. So we're looking for the ones that have the same arrows on opposite sides, and also of course would have to have an arrow going to the right, and the only one that fits that criteria is A. C is also balanced, but it only has arrows up and down, so therefore nothing to the right, can't create any motion to the right. Okay, now we're moving on to Newton's second law. We're on number 6. Newton's second law is all about acceleration. It's the mass is indirectly proportional to acceleration, force is directly proportional to acceleration. It's all about what happens to acceleration. So it is aptly named the law of acceleration. Next so the first demo in this is going to be what we call the runaway car. So essentially we're going to create a car scenario that's going to run away, and we're going to need a couple of books to stack on this ramp, and then we're going to put a wall up here that's going to stop this thing from moving forward, and based on the acceleration of this ramp we're going to have more destruction or less destruction of this wall. So now we need a wall. Bear with us a second while we get a wall. We need something that masks a wall. Here we go. Let's use this. Okay, this box will work for my wall. I will set this right here. First we will start out by putting one book under here. It's going to create a certain amount of acceleration. That acceleration will cause a certain amount of force to be applied to our fake wall here, and we should see the wall displace a certain distance based on that acceleration. So as the car moves down, there we go, and the wall moved. So now we're going to increase the height of the ramp by putting another book underneath it, and that should cause us to have more acceleration, and thus the wall should move further. So let's go ahead and try it out. And you see that the wall does move forward, and we're not going to go any further with this because I don't want the wall flying off the table. But if we move it up higher, we'd have more acceleration, therefore more force delivered to the wall, and you get the point. So in describing this, you had a car sliding down a ramp, increasing the acceleration by increasing the height of the ramp, causing the wall to move a different amount each time. So what happened to the acceleration when you rise the ramp? Obviously it went up. Why did the car do more damage? Because it delivers more force, right? Force and acceleration are directly proportional. More acceleration means more force. More force means more acceleration. And that is can be seen in both the formula and the definition of Newton's second law. Okay, what happened if you had a real car and hit a concrete bridge at a high speed versus low speed? Well, you know the expression speed kills. So obviously the higher the speed, the greater the force, the more damage to you, the more damage to your car, the more damage to the wall. So this is why you want to keep your speed within the safe limits. Okay, let's move on to next, which is a dump truck. So the big old dump truck, number 8. So now we're going to take the same car and we're going to simulate it accelerating on its own with no mass, and then we're going to add mass to it and see how that affects the acceleration. You remember Newton's law says that these are indirectly proportional. So that means as I add mass, I should see less acceleration. So I want you to focus on the acceleration of the car just by itself and just kind of observe how fast it goes. There we go. And now I'm going to create an equal amount of force to the car by depressing this spring, compressing the spring an equal amount each time. And that's how we're going to get the same amount of force each time. But now I'm going to add some mass to the car. And I want you to observe how the car accelerates now that the mass, and we're looking for that inverse relationship. So it should accelerate less. And hit the car, and as you can see, it accelerates significantly less when it has less mass. So Newton's law seems to be holding up fairly well. So added mass to the car, reduced the acceleration. How did you keep the force constant? Same amount of compression on our spring. What happened to the acceleration when you increase the mass? Decreased. Decrease the mass, increase. That's all explained by Newton's second law. You can plug the numbers into the formula and see how that works. Okay, and D, we're going to skip. So again, D, we're going to skip. So we got plenty of opportunity to do math in class, and all of number 9. So the rest of this page we're going to skip. And we're going to move on to number 10. Number 10 is Newton's third law. So the third law is all about the reaction, the action, reaction, and the interaction between two objects that are pushing and pulling on each other. So the prefix inter means between. So that means it's the action, reaction, or the action between two objects. So it's called the law of interaction, which is the action between two objects. Just on a side note, the internet, that would be inter, between, so between the net, which means computers put out data that goes between the network of computers. Just a little side note that I did cover in class, in case you were ever wondering. So this is just a matter of we're going to pull on a spring, and as I pull on one spring with, let's say, 3 newtons, I can look at the other spring and it will also have 3 newtons. If I pull on with 4 newtons, the other one has 4 newtons. So this, and pull on with 5, the other has 5. This shows us that indeed Newton's law that states that they will have an equal and opposite force. So the equal is the important part of this demonstration, is that the forces are equal between the scales. And then if I add a third scale, now I've increased the action-reaction pairs. Now I've got action-reaction between the white and the brown scale, and I've got an action-reaction between the brown and the green scale. And I'm going to pull them all to 5 newtons and observe that all 5 scales are reading 5 newtons because they are indeed applying an equal reaction force to each other as the action force. And so in terms of describing what happened in that, again, hooked the scales, observed that they have the same force. Were the 2 readings the same? Yes. Explain why. Newton's third law. Action, reactions are both equal and opposite. And then what happened when you hooked 4? Again, equal amount of force being applied to each scale. We're skipping 12. This brings us to 13, the last one, which is basically we're going to be hitting a piece of toilet paper, but we're not going to use toilet paper. We're going to use paper towel. So in terms of hitting a piece of paper towel, I can go ahead and hit that paper towel as hard as I want, but the paper towel will only hit me back as hard as it can before it breaks. So I can apply as much of force as I want, but it's limited to the amount of force that the paper towel can apply back to me. That's what Newton's third law says. So this didn't hurt my hand because it could only apply back a very small amount of force. So it didn't have enough force to hurt me, and subsequently it didn't hurt my hand. Now if I hit an object that has more force, and I hit it as hard as I could, and this one can deliver a much stronger force than that paper towel, I am going to hurt my hand. And so that's why I'm going to decline on hitting the wood, because it can hit back with a lot more force. I told a story in class about my brother who got mad at a girl and hit a fiberglass boat, and it broke his hand. And that was pretty silly of him, but what made him an idiot, in my definition, was when he healed from that, he got mad at the same girl, hit the same boat, and broke the hand again. Same hand, same fracture, same, so if you do repeat the same process, you will likely get the same results. Just a little lesson for life for you. So, what did you observe here? Hit the toilet paper, it hit back. The force was limited to the amount of force that the toilet paper could hit back. So, indeed, you can't hit the toilet paper any harder than it can hit you back. So in answer to the question, can you hit harder than the TP? No. You're limited. And did it hurt? Of course not. But finally, let's see what would happen if you hit a brick wall with all your force. You'd highly break your hand. Very highly likely you would break your hand. If not, it would cause a lot of damage. Okay, so that completes the Newton's State Fair lab demo.